Article 310.15 V4 of the National Electrical Code, or NEC, is relevant to a 120/240 volts alternating current three-phase open delta system. Understanding the implications of this article is crucial for ensuring electrical installations meet safety standards and comply with regulations. Let's break down what this means. An open delta system is a type of three-phase electrical power system that uses only two transformers instead of the usual three. This configuration is often employed when the full capacity of a three-phase system isn't initially required, but there's a possibility of future expansion. It's also used in situations where one of the three transformers in a standard delta configuration has failed, allowing for continued, albeit reduced, operation. Now, let's examine Article 310.15 V4. This section of the NEC addresses adjustments to allowable ampacities of conductors based on the number of current carrying conductors in a raceway or cable. Specifically, Article 310.15 V4 states that for three-phase alternating current systems where the neutral conductor is not present, the provisions of 310.15 V4 shall not apply. In simpler terms, if you have a three-phase system and there's no neutral wire, you don't need to apply the ampacity adjustment factors outlined in 310.15 V4. So, why is this important for open delta systems? The key lies in the absence of a neutral conductor in many open delta configurations. Because the neutral conductor is not always present, the provisions of Article 310.15 for concerning ampacity adjustments do not apply. This is because the neutral conductor, when present, can carry imbalanced current, which contributes to heat buildup in the raceway or cable, necessitating ampacity adjustments. Without a neutral, this concern is mitigated. The next important consideration is Table 310.15 V2. This table provides the minimum size of neutral conductors for three-phase systems. However, the crucial point to understand here is that Table 310.15 V2 does not apply to open delta systems, particularly those without a neutral conductor. The reason is directly tied to the statement in Article 310.15 V4. Since Article 310.15 V4 doesn't apply when there's no neutral, the specific sizing requirements for neutral conductors outlined in Table 310.15 V2 have become irrelevant in such open delta setups. In practical terms, this means that when designing or evaluating an open delta system without a neutral, you don't need to adhere to the neutral conductor sizing guidelines presented in Table 310.15 E2. Instead, you'll need to determine the appropriate conductor sizes based on the specific load requirements and other applicable NEC provisions. Now let's delve into some considerations for working with open delta systems. Firstly, understanding the voltage characteristics is critical. A 120/240 volts open delta system typically provides 120 volts from each phase to neutral, and 240 volts between any two phases. However, one phase, often referred to as the high leg or wild leg, will have a high voltage to neutral, specifically approximately 208 volts. This high leg must be clearly identified, often by orange coloring, to prevent accidental connections that could damage equipment. Secondly, calculating the load is crucial for proper conductor sizing and overcurrent protection. Since the capacity of an open delta system is less than a closed delta system using three transformers of the same size, careful load management is essential. The available power in an open delta system is approximately 57.7% of the power that would be available from a closed delta system using the same size transformers. Therefore, it's important to accurately assess the load requirements to avoid overloading the system. Thirdly, ensure proper grounding. Grounding is essential for safety and to provide a path for fault current. In an open delta system, grounding is typically achieved by grounding one of the transformer bushings. The specific grounding configuration should comply with NEC requirements and local codes. Fourthly, consider the potential for voltage imbalance. Open delta systems are more susceptible to voltage imbalances than closed delta systems, particularly under imbalanced load conditions. Voltage imbalance can lead to overheating of motors and other equipment, so it's important to minimize imbalances through careful load distribution. Fifthly, future expansion is another important factor to keep in mind. If there's a possibility of future expansion, it's often prudent to install a third transformer to convert the open delta system to a closed delta system. This will increase the system's capacity and improve its voltage stability. Sixthly, always refer to the latest edition of the NEC and local codes for specific requirements and interpretations. Electrical codes are subject to change, so it's essential to stay up to date with the latest regulations. Seventhly, use appropriately rated equipment. All electrical equipment, including conductors, transformers, and overcurrent protection devices, must be rated for the voltage and current levels of the open delta system. Using undersized or improperly rated equipment can lead to equipment failure and safety hazards. Eighthly, implement regular maintenance. Regular maintenance, including inspections, testing, and cleaning, is essential for ensuring the reliable and safe operation of an open delta system. Maintenance should be performed by qualified personnel. Ninthly, document the system thoroughly. Accurate documentation, including wiring diagrams, transformer specifications, and load calculations, is essential for troubleshooting and future modifications. Finally, prioritize safety. Electrical work can be dangerous, so it's important to always prioritize safety. Follow lockout/tagout procedures, use appropriate personal protective equipment, and work with qualified personnel. In summary, when working with a 120/240 volts alternating current 3-phase open delta system, remember that Article 310.15 B4 of the NEC applies. Because there is no neutral conductor, the ampacity adjustment factors in 310.15 B4 and the neutral conductor sizing requirements in Table 310.15 B2 do not apply. Always consider the specific characteristics and requirements of the open delta system to ensure a safe and compliant installation. Understanding these nuances is crucial for electricians, engineers, and anyone involved in electrical installations to ensure safety and compliance with the National Electrical Code. By paying close attention to the absence of a neutral conductor and the implications for conductor sizing and ampacity adjustments, you can ensure the safe and efficient operation of open delta systems.